Good morning, everyone. My name is Jingjing. My advisor is adult recovery. My project is isolation and recovery of the circulating tumor cells on an unstructured coated microfluidic chip. Here is the outline of my presentation. The research problem: the metastasis causes 90% dies. The tumor cells can invade the surrounding tissues and they enter the blood and they adapt some new microenvironment. They form and adapt, colonize, multiply into the new tissues. This picture shows how clearly the tumor cells form the new metastasis. The circulating tumor cells circulate in the blood, but they are less invasive. They won't form the new metastasis, but they contain the similar genetic information from their parental cells. So we want to utilize this kind of information. But they have the size heterogeneity and they're rare, so we have difficult to isolate them. Also, we want to keep them intact and contaminated when we recover them. Let's go in detail about the CTC. Compared with the high background of the red and blood cells, they only have 1 to 3,000 per millimeter. Also, they have the size heterogeneity. They usually should be 15 to 25 micrometer, but they have the CTC clusters. Some of them may as small as the blood cells. People propose several isolation methods. We want to use the microfluidic affinity selection method. The advantage is that they have the efficiency and the purity, but they have difficult to release to attract a single CTC. In this proposal, we will fix it. So our objective is that how to enhance isolation and recovery efficiency of the CTCs by using the microfluidic device, and what is the better functionalization method to release, and how this device works with the true patient sample. There is a research plan. We collect the patient sample and we made the genetic validation layer by layer, and we added the antibodies and nanoparticles. Then we run the blood to isolate them. After that, we collect the data and analyze it. Here is the whole modification of the device. We biotinylated the gelatin and with triple weighting to help form the coating, and we add the antibodies, the green one, and the nanoparticles, the circle. So the function of the antibody is that they can affinity selection the CTC. We will use a herringbone chip for the device, and here the pattern in the left corner and the pink particle are the antibodies. And there is the antibody we will use in the proposal. Let's go in detail about gelatin functionalization. You have 2 release modules. The first one is thermal responsive for the box CTC with temperature up to 37 degrees C. The coating will degrade, so the CTCs will release. And for the single CTC, we increase the frequency controlled mechanical stress, and it will dissolve the localized single CTC. And here are the results. Figure A shows after the coating, the bottom and the middle plates of the coating, and B shows the identical thickness of the coating. So we eliminate the bad effects of uneven coating on the device. And there is the box CTC release result. Before we do that, figure A shows the lifespan of our coating is over 45 days, and B shows the fraction of immobilized CTCs on the device. You can see after 37 degrees C, it's almost 0. And the figure C shows the intensity of CTC before and after the release. The red one shows it's relatively low, and D shows the position of the CTC with the time. It's a microscopic image, and we right now introduce the results for the single CT release. Figure A shows high yield of the viability and the purity of the result, and B shows the frequency increase, the radius of the mechanical stress will enlarge. Those are results from our previous work, but right now we use the true patient sample. It's very complex. The significance: the CTCs can be used for the cancer prognosis, curative evaluation. They also can be used for the biomarkers for the cancer. They are very important. And here is the reference. That's all. Thank you. Do you have any questions?